So let's continue in this lecture with machine learning, but let's branch out a bit. Rather than thinking just of random forests, which we've covered in the last few lectures, we're going to talk about different types of machine learning models, particularly neural networks. We'll also talk a little bit about logistic regression. And in this lecture, the purpose is partly to introduce these different types of machine learning models, but we'll also have more practice with train test splits and assessing model performance. And we'll also show something that we didn't need to do with random forests, but we do need to do with neural networks, is to standardize our data. The nice thing about machine learning in Python is that most of these models have an almost identical syntax. So once you've done one, once you've figured out random forests, you can do neural networks. They might have different hyperparameters. For example, with random forests, we saw we had a parameter, the number of trees, and that's not going to apply for neural networks. But the number of layers and the size of each layer is going to be a hyperparameter that we'll look at for a neural network. But the basic syntax is the same across all of these, a really nice feature of scikit-learn. So let's load in the same data, the same ADU data set we've used before, and create a variable with the subset of variables we want to use. So this is the same code as we've seen before, and then we're creating this data frame to fit with no nulls and our subset of the data. And let's import these relevant scikit-learn functions as well. We didn't need to standardize our data with random forests, but we do for many other machine learning algorithms. And standardization basically means converting this onto a scale where you have a mean of 0 and a standard deviation of 1. So it means that each variable has an identical mean and a nearly identical standard deviation. So we can't do standardization for dummy variables. These are still going to be 0 and 1. So let's just do this for our others, our continuous variables like lot size. Well, how do we do this? Well, let's use a list comprehension, which is a little hard to get used to, but once you get it, it's a really satisfying and very Pythonic way of passing columns. So for example, in a list comprehension, imagine you want to add a suffix to each of these columns. Well, one way to do it is to create an empty list, new columns, and then let's loop over each of these, and then these old columns, and then append them to our new columns with a suffix of 2020. So we get units 2020, square feet 2020, lot size 2020. Well, this works. There's nothing wrong with this, but it's much cleaner and more satisfying as a list comprehension. So the order here is reversed. So this on the left is what we want to put inside the new list. And then on the right of the list comprehension is our loop. This gets the same result, but it's much more compact and easier to read. We could also add an if statement here to do a subset. So, for example, if we don't want to have units, we could say if units not in col. And what's col? Well, it's going to loop over the values of old cols. So then we get our same output, but we only get it for the elements of our loop where this if condition is satisfied. So how do we do this in our context? Well, let's look at the same syntax. Here we're not transforming this, we're just putting the unchanged column from all of our columns in df to fit. But we're going to use it as if condition. So if the column starts with use type, these are our dummy variables, or use description. Or this is our dependent variable, which is binary, has ADU. If it's any of these, we're going to store it in cols to exclude. So I'm going to leave it for you as an exercise how you would rewrite this list comprehension as a for loop. So pause the video there and see if you can figure that out. Well, if we want to do this as a for loop, notice this is very compact. We could do it the same way as before, create an empty list, loop over the columns in df to fit, and then if these conditions are satisfied, then we append this column to this list, cols to exclude. So we get exactly the same result. So we have a list of the columns that we don't want to exclude. Well, now let's look at the columns that we want to keep in order to again, these are the columns that we want to standardize. So we can use a list comprehension again. So let's do our other cols, so our other cols that aren't to exclude. So let's loop over our columns, and let's return this unchanged if this condition is satisfied, if it's not in this exclusion list that we created. So these are going to be all the columns, other cols that we want to standardize. So let's scale them. Well, let's use our standard scalar function. Now this returns a NumPy array, not a pandas data frame. So the next step we're going to use is convert this array back to a data frame. So what does this mean in practice? Let's import our library. This just initializes the object and the standard scalar. And then we're going to fit it. So what are we going to fit? In other words, standardize. Well, we're going to fit a data frame, but just with these columns here. So this is going to give us a scalar. And then we want to transform it in terms of standardizing it. And what are the column names? Well, these are the names we had before. They just got lost in the transformation process. And then so did the index. So we'll just re-add our index that we had on our column. And then these examples are from the web page here. The documentation is pretty good. So have a look at it and see if you can look at more examples. So then remember, our scaled data frame didn't have the columns that we excluded. So we have a scaled data frame that we created here. Now let's join it back to our columns that we excluded. These are the binary columns of a true or false, and put it back in data in df scaled. So we have our scaled columns, but we also have our original dummy variables, and we should have a has ADU column on the end. So how do you know that this works? How do you know that each of these columns that we scaled does have a mean 0 and does have a standard deviation of 1? I'm going to leave this for you. Pause the video and figure that out. So how do we standardize? Well, let's just use describe. So describe creates a lot of summary statistics for each column. So we can see, well, we have a count. Well, let's look at the mean. Well, these means aren't exactly 0, but they're really, really close to it, e to the minus 16. So all these columns have a mean 0, except for our binary columns, our dummy variables, and our true-false dependent variable, which was at the end. So our standardization worked in terms of we have 0 mean, and it also works that we have a standard deviation of 1 for all of these scaled columns. So that's great. So now let's choose our scaled data frame. We can do the same train test split. And now we can estimate our neural network model. Now we're in the position to do that. So the workflow and syntax, as I said, it's very similar to the random forest as before. We're going to import a classifier. We're going to initialize the object. But just the hyperparameter we have are these hidden layer sizes. And then we'll have the max iterations argument as well. And then we're going to fit it, the same syntax as for a random forest, and we're going to predict it based not on the training data set, but based on the testing data set. Now, what are these hidden layer sizes? Well, this is a way that the neural networks works. And you can think of this as each observation is passed through a series of layers. And each layer is going to get excited if it sees an ADU, and it's going to light up and go like bing, 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 bing. And then it's going to pass that result down to a layer below that, which is going to also light up in the neurons and get excited if it sees something it likes. And it's also going to go bing, 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 bing. And so we have actually 10 layers here, which 10 by 10, cells, each of these. So we're going to pass through this series of neural layers where the neurons are going to light up if it sees a piece of data that it likes. So that's the way that I like to visualize a neural network. Beyond that, it's really a black box. You can't really have a look at the internal workings in the same way as a random forest. You can look at the decision trees. That's much harder to do with a neural network. It's basically a black box. But we can look and see how we did. Again, this will take a little while to run. Your computer fan is probably going to run quite fast. But let's look at the predicted objects. OK, so that maybe took a minute or two for you. Let's see how we did. So we have our predicted variables. Let's look at the classification report, as we did with the random forests. So we can look at our measures for precision and recall, or we can look at the confusion matrix, which again I find the quickest and most intuitive way to look at our predictions. And so we still have this problem, right, that we're predicting a lot of false negatives. The true label is true. There really is an ADU, but our prediction is false. We are getting 152 of these ones where we're predicting a true value. So we do actually get pretty similar results in aggregate to the random forests. And again, perhaps this indicates something of the inherent unpredictability of ADUs, given that this is a relatively rare event. Or perhaps we can do better, either with additional parameters, additional variables, or we could adjust for hyperparameters. In particular, what if we have more layers, or we have larger layers in our neural network, rather than have 10 by 10 by 10? This is something we could experiment with these different layer sizes and see how that affects our predictive performance. One point of comparison is useful to do with logistic regression, which you might be familiar with from stats class. This is the same logistic regression as you may see in stats. Here we're just thinking about it in a predictive sense. Logistic regression is also implemented in scikit-learn, and the syntax should be familiar with you. And standardization helps, so we're going to use a standardized dataset, which we already did for the neural networks. So let's initialize the object, let's fit the model, and let's predict the result. So notice we get an error here. It doesn't even, algorithm failed to converge. The total number of iterations reached its limit. And this is probably because methods like logistic regression really don't handle highly correlated variables very well. If you remember, we threw in the kitchen sink to this model. We threw in all these subcategories of agricultural uses, of number of bathrooms and number of bedrooms, and very correlated variables are fine for a neural network or a random forest to deal with. It throws out the ones it doesn't need or doesn't consider the ones it doesn't need, but it's hard for logistic regression. So let's see if we can do better with a smaller set of predictors, without some of the detailed dummy variables. Let's do the same as before. And our confusion matrix, well, this is a pretty terrible model, right? Out of these 6,207 ADUs, we're only getting one prediction right. So while our machine learning random forests and our machine learning neural nets may not look great in absolute terms, they do look really better by comparison to a more traditional logistic regression model. So we're going to leave our machine learning classification discussion here. But I want to reinforce that there are several different ways to do this. Random forests and neural networks are two of the most popular, but there's gradient boost algorithms. There's lots of others that you can explore in the scikit-learn documentation. Because scikit-learn, once you've learned one, you've learned most of them. There's a consistent syntax. Initialize the object, fit the object, predict your results, and then interpret and analyze your predictions. So once you've done one, others are much simpler to assess.